So today we're talking about volumes of solids that have a known integrable cross-sectional area of something. So the question is, what in the world does that even mean? Okay. So what does it mean to have an integrable cross-section? Well, something, let's say, like a cylinder. I'm going to draw it on its side here. Here's a cylinder. If I take a cylinder and I slice it vertically, if I've got it laying on its side, like a toilet paper roll or something, right? It's just laying there. You slice it and you open it up. What do the faces of this look like?
Circles.
It should be circle. This has cross sections that are circles. What if, I can spell circles, there we go. What if it was, let's say, a cone? Similar idea, right? What if it was a cone and I were to slice it perfectly vertically there and open it up? What would each side look like?
Also circle.
And then
They look like circles, right?
yes.
What if I had, I don't know, something like I don't know, suppose we have this triangular prism and I were to slice it and open it up, I should be getting
Triangle.
triangle. Suppose I had that doesn't look good at all. How about, suppose I had I'm not going to draw this at all. Suppose there we go. There's some sort of square pyramid, right? Suppose I were to slice it perpendicular to this base of it. What would I get? Should get squares, right? These are what we call integrable cross sections. In the case of the cylinder or this triangular prism, each of the cross sections are all identically sized, true? But in the case of the cone and this square pyramid, each cross section has a different size than the rest of them. Would you all agree with that?
Yep.
Yeah. And so what we're going to be able to do is we're going to be able to take not just these nice regular pyramids and cones and prisms and cylinders and slice them and find their volumes, but we're going to be able to take things that might be irregularly shaped on the outside, but still have these integrable cross sections. It still have that same shape no matter how you cut it and open it up. You'll always get a square or a rectangle or a circle. But the, I guess we call this the height of it, sort of, or the lateral version of it might look weird. It might have some sort of circular something to it, but when I slice it, I might still get squares no matter what. These are very difficult sometimes to conceptualize what they look like. If we were in the classroom, I have a little model of what one of them sort of looks like. You could think about it let's say I had a semicircle here maybe. And as I went back to form some other smaller semicircle back here, right? These have these linear pieces going back, right? And I've got this other semicircle back here. So it's kind of that one sort of looks like a tunnel. But maybe instead of these being straight lines, maybe we've got something that's doing this on both sides, but each time I slice it, it's still a semicircle, but it's got weird curves to the sides of it. Does that sort of make sense, the shapes that we're going to be looking at?
So that would still be an integrable cross section right there, that shape?
Yes, because no matter how I slice it, we're going to say that every piece along here is still a semicircle.
Okay.
So that's what we're sort of looking at. And so all we're going to do is we're going to find a formula for the area of whatever the cross section is. So in this case, it'd be, a square, x squared, or, the length squared, or here it'd be the, since circles, it'd be pi times the radius squared, or here it'd be 1/2 base times height, or here it'd be 1/2 pi times the radius squared, because it's a semicircle. We'll find that formula for the area, and then we're going to, if it's not already, but usually these will already be placed on an axis for us, we'll find our limits of integration and just integrate the area formula to find the volume, right? And so the way we'll do that is we'll say, each time I slice this, what do I get? I get a little disk, or I get a little, a semicircle which has a very small thinness to it. I'm going to slice it an infinite number of times on the interval from A to B, right? So I might get a circle or a disk with a tiny thickness to it. I might get, a square that has the tiniest little height to it. And each of those tiny little heights or thicknesses of it will be our dx, and then our area formula, and then our integral from A to B. Does that sort of make sense what we're doing? Or it's this idea of summing together all of these things on our interval, just like we sum together a bunch of little rectangles that have tiny little areas. Well, here we're going to sum together a bunch of disks, or half of disks, or tiny little triangular prisms, an infinite number of them from A to B. And they have a volume, which is their area, times the thickness, which is dx. And so if we sum together all the little volumes of each of those little pieces, we should get the total volume of the entire thing. Conceptually okay or no?
Yeah, conceptually.
All right.
Yeah.
Let's try it then. So take a second, read through this first one, and then we'll work through it together. Okay, sorry about that. Everybody good and ready here?
Just a little bit.
What? Is that a yes or a no? I couldn't understand what you said.
Just like 2 more seconds to write down the problem.
Yeah.
Okay. Everybody good now? Okay, so what we're going to do is we're going to try to sketch this curve first. So 2 square root of sine x from 0 to pi. You may or may not know what that looks like. It's not a huge deal if you don't. We can just look real quick. 2 square root sine x, right? From 0 to pi. It just looks like this sort of looks like a semicircular shape, right? It's not sort of semicircle, but it sort of looks like one. And we're just looking from 0 to pi. So we now know what this looks like. Looks like this, basically, right? Goes up to a height of 2. And this is y equals 2 root sine x. And so what this is saying is that this region that we've drawn here from 0 to pi is actually the base of the solid. So imagine coming out of your screen right towards you is the solid. And if you were just to be looking straight vertically down on it, this is the, this is what the footprint of it looks like. This is what the outside of it, the outside of the region on the ground looks like. And if you were to draw a pencil around the object, that's what you'd have marking on the ground or on your screen. Everybody good there?
Wait, so you're saying the object is like protruding out at us? Is that what
Correct.
you're saying?
That is correct. Exactly. Yes. And so the way that this particular object, which is again a very difficult to conceptualize one, the way that it protrudes out of the screen towards you is that the cross sections are squares and the bases run from the x-axis to the curve. So coming straight out, that's not straight out of the screen at you. Maybe if I draw it this way, right? That doesn't look good. Let's try it this way. Every place along here from the x-axis to the curve, there is a square sticking out. So if you were to slice this thing vertically and open it up, both sides of the faces that you'd be looking at would be squares. Right? So effectively what this is sort of doing is it's got this tiny little square that comes out here at the bottom. You're going straight up off of the base in all of these places from the entire curve. You're also going straight up here. But depending on how high up you are away from the x-axis, so what the height is, it depends on how high out of that screen you're coming towards you with that square. And so these squares are smaller because this height is smaller than these ones. Right? And you get all the way up to here and you have these much larger ones. And I think it's hard to conceptualize it, but you could, imagine it being like, I know these are squares, but imagine it being a bunch of differently sized dominoes, right? That were very, very thin, that were sticking straight out of the screen towards you, right? And instead of being rectangles like dominoes are, they're squares. Right? And so it's just like a bunch of them lined up together of different heights and different widths based on this function. Does that make sense? Sort of what it looks like?
So how did you determine that it's protruding out at us instead of being another way?
The base of the solid is this region. I mean, it could be going into the screen if we wanted to. That would be fine too. It could be going away from you straight through the computer or whatever you're looking at it on. But I think it's easier to think of it as if it's coming out at you because it's the base of it.
So that what we just drew is like going to be is it going to be like the area, and then we have to.
Correct. Each of those squares represents the cross-sectional area. And so what we're going to do is we're going to take each of those squares, which we can find the area of it, right? This area of the square is just x squared, right? Or, the side squared. And we're just going to sum together an infinite number of those squares from 0 to pi. And they each have an infinitesimally thin thickness to them. And we're just going to sum together each of the volumes of each of those little squares. So it's the area times the thickness. And so how thick is each one of these squares? Are they thick or are they thin?
Which way did you cut the solid to get those squares? Like, did you cut it vertically or horizontally?
Perpendicular to the x-axis, vertically, yes.
Is that how you always cut it?
No, the cross sections are squares with bases running from the x-axis to the curve. That's how we know that the base of this square goes from the x-axis to the curve. And so then it's going to come out that same amount and up this same amount across the top. So if we just slice it vertically and open it up, we'd end up with squares. If I had said something like, and I'll draw it over here, if I had said something like yeah, I would have had to have said that the cross sections extend perpendicular to the y-axis for it to be like this, and then they'd be coming out at you like this.
So like what shape is this gonna form, or is it forming? Is it like a semicircle cylinder kind of thing, or does it not
Well,
matter?
It doesn't exactly matter. There's no name specifically for it. It's forming a sinusoidal type curve as the base with squares projecting from it. I mean, that's the only way to really describe it. That's what it's doing. That's what it is. It's not something that you've ever physically held in your hand. It's not some shape that you've dealt with in a math class before, or that I could just pick up an object in the house and be like, it's a there just isn't one. This is why people struggle with this concept a little bit. We all okay so far or no?
Yeah, a bit better, yeah.
All right. So what is the thickness of one of these squares? First off, is it really thick or is it really thin?
And an infinitely
Really thin.
Right, it should be infinitely thin, right? Okay, well, in which direction is it infinitely thin?
X-axis wise, like,
Right, it's infinitely thin in the x direction, and so we will call that a thickness of dx. What is the area of one of the squares? Just in general, the area of a square should be side squared, right?
yeah,
Okay. Well, what is the side? What is the length of one of the sides?
is it dy?
It is not dy.
Just change in y?
It is
The
fact, it
2
is just-
times yeah, it's just the function.
It's just the y, right? It's just that y. It's just 2 times the square root
Yeah,
of x, because that's where our bases go for our squares. They go from the x-axis to the curve. Whether I'm at this x value, right, or this x value, or this x value, the height or the side length is always 2 square root sine x. And so our cross-sectional area should be s squared or y squared or 2 root sine x squared, which is 4 sine x. And so that should tell us that the volume of one of these pieces is 4 sine x dx. Right? It's the area of that square times the thickness of the little chunk that we've got there. Everybody good with that?
does the dx just represent that it's like infinitely small? Is that all that it pretty much
It
means?
represents that it's infinitely thin in the x direction. And it also tells us, since we're going to do an integral with this, that our side length or our area formula has to be in terms of x.
Okay,
So
so
if
it doesn't
was
mean like
infinitely
change in
thin-
x,
Say that again.
it doesn't mean like change in x or anything like that? Or
I
like-
mean, it's not a change in x, no, it's the infinitely thinness of each of those squares.
Okay, thanks.
Okay, and so now we've got the volume, which is the area times the thickness. And so all we need to do is integrate from 0 to pi 4 sine x dx. And what's the integral of 4 sine x?
-4 cosine x.
Exactly, evaluated from 0 to pi, which should be -4 cosine pi minus -4 cosine 0, which is what? Cosine of pi is -1, right? So -4 times -1 is 4. And then minus another -4 should be 8 units cubed. Does that make sense or no?
Can you explain why 4 sine x dx is the volume of one piece?
Yeah, so we'll go back through that. So the volume, so each of these little squares that we're drawing, right, has this tiny little thickness to it. Right, because we can't slice something infinitely thin, and even though we'd like to slice it infinitely thin. The dx is the thickness. So it's telling us that we are slicing it as thin as we possibly can in the x direction. So the thickness is the dx of each of these square pieces that I'm chunking this out into. And then the area of the base of this square, right? The area of this face that we've got here is just the side length squared, and the side length is just the height of this function, because each of these little squares has a side length that goes from the x-axis to the height of the function, which is 2 root sine x. And so our side length is 2 root sine x, which tells us that the area is that squared, or 4 sine x. The thickness of it, find the volume of a tiny little square prism, you take the area of the square and multiply it by the thickness, so that's 4 sine x times dx.
All right, thank you.
Yep. Any other questions on that?
I think you just cut out for a second there.
Yeah, I was talking to my kid. Sorry. I thought I finished. I was just asking if there's any other questions on it. Maybe you didn't hear me say all that. Okay. No questions there? What if instead of having squares as the cross sections, we had equilateral triangles? So that would mean that, let's do this in a different color. Everywhere across here, I've got an equilateral triangle sticking straight up, which is going to give us some sort of object that's sort of got like a curved ridge to it at the top here. And it's got these sort of flat-ish sides, but curving up and then back down. That one might be a little easier to visualize than the square one, maybe, because it's got a ridge across the top. But conceptually, are we okay with that?
Yeah.
Okay. What is the thickness of one of these triangles?
Dx.
Thickness is still dx, right? Because they're still running from the x-axis to the curve. The area of an what's the area of an equilateral triangle?
1.5 base times height.
Okay, yeah, that's true. There's an even better formula. That is specific to an equilateral triangle that just deals with the side length. You can use right triangle trig to prove it. But if you just know it, life is a lot easier.
So like side times, I don't know.
If you don't already know this area formula for an equilateral triangle, memorize this formula for an equilateral triangle. The area of an equilateral triangle is the side squared times √3 divided by 4. So if you didn't already know that now. And what is the side length for one of these equilateral triangles?
2 root
Just-
sine x.
Right.
Yeah.
And so our volume for one of these little triangular pieces, for one of them, I'm going to put it inside my integral because we're going to sum together all of them from 0 to pi. The volume of one of them is this squared, which is 4 sine x, times √3 over 4. So the 4's will cancel, so it's just what? √3 sine x times the thickness, dx. Good or no?
Good.
Okay, so we'll
Good.
just integrate. √3 times, to do the integration, negative cosine x from 0 to pi. And negative 2 sin x from 0 to pi becomes what? Positive 1 minus negative 1. And so we end up with 2 root 3 units cubed. Any questions or issues there?
So when we do equilateral triangles, is it almost always we're just gonna have like a side length? We can never use 1/2 base times height. We're always gonna have to use the sine squared times root 3 over 4.
I mean, generally, yes, if you're given an equilateral triangle, but I might give you a, an isosceles triangle. In fact,
Okay.
we'll do one later that uses an isosceles triangle.
Okay.
But yeah, so this one's just convenient because then you don't have to do the right triangle trig to find it all in terms of this one side length. So if you just know it, it's probably better. Any other questions on any of these two before we move on to another one? Okay, so we've got a paperweight. Paperweight is made so that its base is the shape of the region between the x-axis and one arch of the curve y equals 2 sine x. That looks about the same as before, right? Where does 2 sine x hit the x-axis? Besides at 0. Also at pi. Okay. And we have cross sections that are perpendicular to the x-axis, which are semicircles. So perpendicular to the x-axis means the semicircles will be going this direction. So coming straight out of the screen right at you are, if you could slice it an infinite number of times, an infinite number of these little semicircles sticking out at you. So it's curved around the top, it sort of tends towards the upper part of it as it goes through, right? There's not quite a ridge because there's no points, but the sort of hump of this thing goes up and then back down towards the point at pi. Everybody okay with the picture I've drawn?
Are the planes facing us?
So if you were to slice it perfectly vertically and open it up, you would have a perfect semicircle. They are sticking out of the screen directly at you, as if the screen is the face of a table and you've got this thing sitting directly on it. And it's flat on the bottom, like your screen is, but it's coming straight out of the screen as semicircles at you. Does that make sense?
I'm not really understanding.
Okay, so you know what a paperweight is, right? It's just like a flat thing that you put down on something, right? So your screen is, pretend your screen is the table that you're setting the paperweight on. And coming straight out of that is the paperweight, right? And if you were to take that paperweight and slice it vertically straight down the middle or at any place straight vertically and open up the two pieces that you got, the two faces that you would be looking at would both be semicircles. So you have semicircles that are popping out of the screen directly at you.
Okay, I think I understand now.
Okay. So first off, we need to figure out what the thickness of each of those semicircles is. And since they are perpendicular to the x-axis, what should the thickness be?
Dx still.
There'll be dx for this one, right? They're perpendicular to the x-axis. The thickness of each of the little pieces will be dx. What is the area of a semicircle?
just 1/2 pi r squared, right?
1/2 pi r squared. And so what we need to do is we need to integrate from 0 to pi 1/2 pi r squared dx. Okay? Because that's the area times the thickness. Okay? And the area times the thickness should give us the volume of each of those little tiny pieces. Good or no? So can we integrate it as it sits right now, 1/2 pi r squared dx?
No, we need to find r in terms of x.
Right, we need to find r in terms of x. Well, these are semicircles, so the radius would be from here to here, right? Or from here to here, right? That's our radius. The radius is, in terms of y, it's half of y, isn't it?
Yeah.
Yeah.
Or half of two sine x. Agreed?
Could you just make that sine
Yeah.
x?
Okay. So yeah, we'll just make that sine of x, definitely. And so all we'll do then is plug this in. We now have a pi over 2. It's a constant that I could pull out, times an integral from 0 to pi of the radius sine squared x dx. Good or no?
Yeah, good.
Okay. How do we integrate sine squared x dx?
Could we do like a simple u sub or no?
Nah, that'd be cool if we could. Pretty sure we did one of these way back when. We used the power reducing formula. Right, we can reduce the power of sine squared x to 1/2 of 1 minus cosine 2x dx. Which ought to give us pi over 4. Now times an integral from 0 to pi of 1 minus cosine 2x dx. And what's the integral of 1?
X. Just x.
And what's the integral of negative cosine 2x? That one requires a little u substitution. Hopefully we've done enough of these ones that are very similar to this that you can tell me what that is without having to write out the u sub.
Oh, 1/2 sine 2x.
Right, minus 1/2 sine 2x. And that needs to be evaluated from 0 to pi. So we'll just plug those values in and figure out what we get. So we got pi over 4, we got pi minus 1/2 the sine of 2 pi. And then minus 0 minus 1/2 the sine of 0. I plug those all in there, pi 0 minus 1/2 sine of 0. Yep, okay. Everybody agree with that? And what do we have? Pi minus what? What's the sine of 2 pi?
0.
And 0 is 0, and half of the sine of 0 is 0. And we end up with the volume of that shape is pi squared over 4 units cubed. And in fact, I think it said inches in this problem, so we'll call it inches cubed. Good or no?
So with that power reducing formula, is there like any other way to do it like conceptually, or do you just have to work through that equation? Like there's
Yeah.
no other way?
You either have to use the power reducing formula, or you have to know how to do integration by parts, which you don't know how to do, to come up with a power reduction formula. Not a power reduction formula, they call it a reduction formula for sine of x, which is a lot more complicated. That's the only way to integrate that, is to know the power reducing formula.
So
It's on
same
the
thing
treat
with,
sheet. One of the ones that I told you guys you should definitely know. Off the treat sheet.
okay. Same thing with like cosine squared x, or like,
You should know the cosine squared x one also. The tangent squared one's less important because you can always do the sine squared over the cosine squared if you need to. So at least know the sine squared and the cosine squared power reducing. They're almost the same, right? The sine squared one is 1/2 of 1 minus cosine 2x, and the cosine squared is 1/2 of 1 plus cosine 2x. So it's just differ by a sign. But definitely know those.
okay. And will that be fairly common with our volume problems using that?
Yeah, it'll, I mean, fairly common. I don't know. It'll pop up every once in a while. Common enough that you need to know it. All right, let's do another one. Let's do this one in terms of y, which you'll note that as we go through here, we'll say the cross sections are perpendicular to the y-axis this time. So we've got the base of our solid is this circle. X squared plus y squared equals 1. And now we have cross sections perpendicular to the y-axis from -1 to 1 that are isosceles right triangles with one of the legs stretching across the disk, which means that anywhere I go, I've got an isosceles right triangle with one leg stretching across, sticking straight up out of the screen, or straight out of the screen towards you. So here, same thing. Right here, same thing. Everywhere along here, we've got these isosceles right triangles. Another one of these ones that has this ridge that sort of curves around the left-hand side of this and has this like slanted side on the right. Good or no?
So those points are sticking out at us again?
Everything we do is sticking straight out of the screen at you, correct?
Okay, that's how always, okay, okay.
And all these ones that say the base of it is something on the x-axis or in our coordinate plane. If it says the base is in the coordinate plane, everything is sticking straight out of the screen at you.
Okay, thanks.
All right. So what are we going to do here? We need
Do
to
what
figure
we've done
out
before.
what?
To do what we've done before.
Yeah, what's the thickness going to be?
Is it dy this time?
This time it's dy because we're going in the y direction here. And what is the area of one of these triangles? It should be 1/2 the base times the height, right?
Yeah.
Well, the base and the height should be the same, right? Because these are isosceles right triangles, right? That's what we were told. So we just need to figure out what the length stretching across here is. So what is the length stretching across here?
X.
Not quite. So where do we measure x from? We measure x from the origin, right?
Is it 2x?
Yeah, so this side of it is x, and then this
Oh, yeah.
it should also be another x. So the base ought to be 2x. And since they're isosceles, that should tell us that the height is also 2x, which should make this 1/2 of 2x squared. Everybody agree with that?
Yeah, that works.
All right, which simplifies to what?
Just x squared. Or,
2x squared, right?
Yep.
But the problem we've got now is we want to integrate from y equals -1 to y equals 1 to x squared dy. Well, we can't do that, right? Because we have an x and we have a y inside of our integrand. So what should we do then? Try to turn
either, yeah, the x into
our
a y.
x's to y's. And we can do that pretty easily by just going back to our original equation. What does x squared equal? X squared is 1 minus y squared. So we can pull the 2 out and integrate from -1 to 1. X squared is just 1 minus y squared dy. That should now be a pretty easy integral. Y minus y cubed over 3. I don't know why I wrote that all up there. Should be like this. From -1 to 1. Which gives us 2 times 1 minus a third minus -1 minus -1/3. And what does that give us? 2/3, and then minus another -2/3. So 2/3 minus -2/3 is 4/3 times the 2. Should be 8/3 units cubed. Good or no?
So you never want to like change the limits of integration to x or anything like that instead of changing the x to a y.
Correct. You have to turn it into terms of y for this one. And the sole reason for that is because the thickness of each of those pieces is dy. There's no way to turn dy into dx. We can't do that.
Okay.
Can you explain how you got the 2x for the base?
Yeah, so we're measuring across this circle, right? And so starting at the origin or starting at x equals 0, to the right, however far over we go to be at our circle is an x distance. Right? And since it's a circle, it's symmetric on both sides. So the entire length across is x plus another x. No matter where I'm at, suppose I'm starting here and going across. Well, now that's x. And this is also another x. And so they're always going to be 2 x's. They're identical on both sides. And I'm measuring from the center where x equals 0 to my function. So anytime you measure from the y-axis to your function, that distance is always x. Does that make sense?
Yeah, thank you.
Uh-huh. Any other questions there? Okay. So let's do this last one. This is where we'll stop today. Let's see if we can find the volume of a sphere. Actually, let's not. Let's stop right here, I think. 'Cause that's going to get me into more of the next topic that I want to talk about next time. I think it'll be better if we just stop here. Anybody have any questions on the 4 or 5 problems we did today?
Are we gonna have a worksheet tonight or no?
Oh yeah, you will.
Okay. And is
Definitely.
it just gonna be on this or are there gonna be problems that we won't be able to do?
It will just be on this.
Okay.